And we stopped at this part over here, basically, last time. I forgot to get my tablet open, so this is going to be a little bit awkward. So first thing we'll say is, again, all credit goes to this person over here, Dr. Sanchez, because I am a student that's just studying this, so I just want to just record myself do it. Is that all credit goes to this guy, basically. Oh, and Dr. Centillion, because uh, he taught me all of index notation, basically. I'm going to add more stuff to it, basically. I was doing energy before I realized a better way to do it is show what we're doing over here and translating it over here. I think I forgot 1.5. Oh, no, 1.5 is this. That's why I skipped it. 1.5 is this, but to basically the beautiful um where's energy equation? Uh, Density dE. The energy equation is the one equation that I don't have memorized yet, which means I will be memorizing this sooner or later in this class, probably. Because I can't see oh, that's much better. Why haven't I been doing that? And that is better. Okay, here we go. I'm starting to learn how to make the use of this board better. So this is like this plus tau double bar because it's a tensor. And then it is this. Okay, I know what that is, luckily. Um, you can thank Dr. Centillion for that one. So this basically means I never understood this format. So we're gonna go back. Again, I need to disable this somehow. We have to go back to index notation for me to even make sense of this, not this huge equation. Um, we're gonna, oh, it looks way better. Okay, so let's just go back to index notation. If it's index notation, we know this is ij, right? And then we know that this is a partial, and we know that v on top is I and j. What that actually entails as saying is summation 3 I equal 1, summation I equal 1, 3 j of tau ij vi vj, so you can kind of get the sense of what's going on here. Did I do this wrong? Yes, it's x. In this sense, you can see that this is just saying, well, v1, let's start with let's work in out. So you see that we're starting with j, so and we're adding with I, j. Let's start with how we add this. So we start with the inside add over here. So we're going to leave out the 3, I equal 1, and we're just going to do this tau. And we see that there's an I, and there's a 1, 2, and 3. So we can just say 1, and then we can say, okay, that's V1. I think this is right. Tau I2 Vi. If I'm wrong, just shout it out at me later, like this. And then so on. So there's only 3 of them. So tau I2, and that's why there should be 6 terms, or there should be 9 terms although. Did I do this wrong? I might have done this the dumb way. There's supposed to be 9 terms. Vi, oh, this is 3. X3, okay, and then this is supposed to then be equal to writing tau 1, 1, V1, X1 plus tau 1, 2, Vi, Vx2 plus tau 3, 3, tau V 3 divided by tau X3. Now here's a little bit of a sanity check. Let me just show the useful version real quick. Now tau ij is equal to mu parentheses vi divided by this. I should have explained it. Mu. Let me think. It is gradient v plus gradient transform v. This goes up here and then like that. But you get the point. Density v j density xi parentheses. What's going on? You're following me, right? No, you're not. You're not following me. You joined. Okay, there we go. You're following me now. Okay, thank God. Sorry about that. Yeah, you're following me now. Good. I was a little worried. I wasn't following for a second. Now with this, you have to do plus mu b plus 2 divided by 3 mu, and then this is going to be delta ij bk density, not density, which is this vk xk parentheses. What else is there? Density vi vj xj. I have this in memory, and this is actually equal to the double tau. What's it called? Density v divided by density x. Why did I call it density? I don't know. I think it was this actually. Yeah, so that was what it's called. And now we can now show some patterns here that are more intrusive to to understanding, I think, in my opinion. Actually, now thinking about it, this is actually useful, this top portion. Never mind this part. On to the next portion, which is this thing. This should give me something unique, honestly, but I don't see it. Um, um, the thing is, it should give me something arbitrarily completely. I mean, it is. Oh, something's wrong. Something's terribly wrong with my explanation. Um, yeah. No, I just bad handwriting. That's I. That's a. So what we're gonna do here is do this one and this one next, which is gonna be a pain in the ass because they're actually large headache. So VI and then VI divided by those two, right? And you can see that they're the same thing. So what that tells me is a derivative and everything. So imagine this. Imagine moving alongside. This is actually pretty easy. What's happening is of what was it called again? Density VI xj, density VI Vxj, which equals density V Vx, density Vx plus no, U density V dy plus density V. Oh my God, I am not doing this correctly, but you can kind of see what I'm trying to do. I'm trying to expand every term, and I'm just shitting in myself in the foot by not doing numbers because I'm a lazy motherfucker, and I was about to do lazy. Okay, let's do the hard way because that way is actually correct. And we will do it this way. Density V1. We're doing I already here. Density X1, density VI, density X1 plus density VI, X2, density VI, X2, right? I'm doing it correctly. Plus density VI, X3, and then we move on to the big one. We make it into this, which will give you V1. We can't do that, but I'm too lazy to delete anything. So X1, plus density V1, X2, density V1, X2, okay, plus density V1. I think we're good. If we're not, then I don't care. Someone can yell at me later on that I'm wrong. I genuinely think this is someone can yell at me moment. Density, I believe it's V1, density X2 square plus density. I do care. I just pretend I don't. Density. I think I screwed up. What did I do wrong here? We already did density 2 over here. So that's the X3, right? Then we forgot that. So see 9 terms, okay? Density V1, I forgot the X3 one. And then we forgot the density V2, V1, V2 for density X1 squared plus, okay, 1, 2, 3. I think it's V3. Density V3, density X2 squared. Okay, we got that one. All right, the other one now. What kind of pattern will this be? You know what? I'm gonna just look at my notes to figure it out because I remember having this before. So, yeah. Or I'm too lazy to do that too. Okay. What is the difference between this and this? What would happen with the difference between those two? There'll still be 9 terms, right? 9 terms. There'll be yes, I think we have that. Now we need to know the other combinations. Which think about it, it's just a flip of these two, right? The 2 1 goes up here. So what will happen is that there'll be instead of a multiplication, it'll be just density. I keep on calling these D's densities. I don't know. It looks like density. If you look at this D into 180 degrees, it looks like density. So I call them densities for some reason. Not that it matters. I mean, you can, and then X V1, right? And then there'll be V2 density. So okay, I'm going density again. Okay, so it's what's it gonna be? It's gonna be X2, and then this is gonna be X1 and so forth, and there should be 6 of those. Yeah, so we got them. And now that I have the final version written down somewhere else, am I forgetting something about this equation? Parentheses negative k t. So that's the easiest part. That's not hard. I mean, it's hard to compute in actual reality. Oh, I take that back. It's hard conceptually, but whatever. It's fine. So just plug and chug over here. We got that. What else do we need from here? We can expand this term, but that's it. So yes, in reality, the reason why I'm showing this one off is that it's confusing, but at the end of the day, it's just a bunch of velocities with a few constants over here, and you're good. So I'm gonna consider this cha-ching and move on, I think, unless I have something that I forgot. Done with this, pretty much. I'm not going back to that. And this is quite self-evident. This just states that density, ideal gas law, right? Pressure divided by RT is ideal gas law, and R equals R prime over molar. And we all know that, but we only think of air. That's why it's a little bit weird. And then E, I actually never knew this, but there's a E. Oh, the first time I've seen that, which is interesting. Anyways, obviously the equation 1.3, which is non-radiochemical flows, can be alternately expressed by entropy. Okay, so 1.3. Okay, so clearly we need this equation to get into this form. Okay, so let's do it. How do we do this? So obviously, I think I know how, but we will just do it right now. I guess that's not bad. So it's not as bad as doing this stuff. Let's take a. Well, I want to consider that cha-ching and move on because I'm too lazy. All right. Not because that's actually just midnight. That's why. It's New Year's Eve, so just yeah. Anyways, we're moving on to here, which is gonna go from so where's the equation? Density dE dt equal negative this pressure plus that tau this plus no, this is the pressure equation. This is wrong. Yes, that's the momentum. Moving on to momentum for some reason, which is not right. So this is negative p v dot v this plus this tau dotted by v dot minus q dot. Okay. Okay, from this we can identify something here. We can do h equal e plus p divided by rho, and I think this is equivalent to saying e equal h minus p over rho, right? And then you can say this and plug it back into here. That basically says d parentheses dt is h minus p minus density equal negative p v that plus tau double tau. My question is, I thought density has to be inside, but I guess density is quite not compressible yet, which is fine. I know. Over here, moving on to here. Now that I think we need to prove it a little bit. Not because I don't trust it. I actually know it's true, but I'm too. I just want to because I don't know actually because I'm lazy. No, because I'm doing more work. No, because I'm a shithead. Yeah, that's the right word. I'm a shithead. Okay, no, that's the right terminology there. Density, and then we have density, so that equals cancel out. And then we have basically v dot p in 1 minus h divided by density. And we can kind of see that this thing would be v dot h and then minus v dot p. Okay, yeah, so that works. So it is dh dt minus dp dt equal tau vv minus v dot q. And I'm going to do a QED or cha-ching because either one works. Okay, so we got that right. Now let's go into here and move on to the next equation, which is 1.8 over here. We get over here by plugging this equation here. So what I'll do, I think, is say T ds equal dH minus dP over over density. Okay. Yes. So how the F did he do this? How the F did he do this? I'm confused myself. Let's not confuse myself. So because it's a direct derivative. I think he did a dH and then he did a equal to TdS plus dP density, right? Because we know this is true from thermodynamics. We move it to this format. We put it back into here. Then we know it's density d dt parentheses T ds plus d. Let me just do it. P divided by density minus dP dt. Okay, this is making less sense than before. Yes, because this is dH, so this goes away. Now let's leave the 1 divided by dt, which I know is not correct, but I'm assuming that there's an explicit dt, which means this goes away too, I'm assuming. That's the only way this makes sense. And then, no. This is dt over here getting a big D, because the big derivative should work. And then over here, I'm assuming dt goes in here. So this moves on like this. Okay, we got that. We understood that now. Okay. We'll probably forget it in like 5 minutes, but we got it. And then we have tau double bar vv minus v dot q. This. Okay, we got this. We know this part. We can safely know that one. I don't know why I crossed it. That was just my mistake. I should have just. And then something's wrong here because I'm noticing that there's no density here, which cancel out here when you do density. So these two cancel out. Like a good thing. All good things must come to an end, right? Which equals tau double bar that v this minus, and then we have dot over here, and then we have parentheses k delta t, and we have a cha-ching, and we have a QED. Either one works. Anyways, from this, you're supposed to be able to get what? Yeah, I don't think that because I'm confused. What is H equal EO plus CPT, and then we're supposed to ask SO divided by CV. No, no, please. CV equal ln P over P alpha. I am just confused. I don't know what that is. But yeah, so the only confusing part is 1.9. Don't know what it is. Everything else I got. So chapter 1, we're skipping on now. Let me just read this. The term equation of state can be written as entropy and entropy. Entropy and entropy, as where CV and CP are specific heat at constant volume and at constant temperature for the gas with gamma equals CP divided by CP. According to 1.9, a flow is effectively isotropic when the okay, so this is basically zero thing. It's basically saying this equals zero and we're good. Okay. The speed of sound, beside the entropy and entropy, another harmonic constant from dynamics is the speed of sound. A, which is a velocity at which a small pressure perturbs propagation in a compressible medium at rest. To compute the following, this has to happen. Sure, that's true. For specific gas straightforward differential of the second equation. Oh no. Oh no, we're using that. I don't know where this came from, although. Yeah, whatever. I know what this is, although. This is the, okay. So we have S minus SO divided by CV equal ln P over P alpha, which shows me that we can get this over here, right? If I know correctly. And I'm supposed to take a partial derivative. Okay, so I'm assuming you have to do e to the S minus SO divided by CV equal P over P alpha. And we can take a partial derivative of that. And what is this assuming? Perfect gas straightforward division of 1.9. 1.5 is in two different things, so CV must be 1.7. We'll figure it out. Right? We have P alpha there. But we have E S minus SO divided by CV. That's what we're saying. Okay, we got something. The derivative of this rho, which equals to rho P alpha. Not P, it's rho. Stop that. It's not cool. Tablet. And then we have, is there a density in S minus SO? No. But ES minus SO divided by CP. Okay, we got this. But this over here is equal to saying P minus P rho, which is equal to saying, that's E, right? But something's wrong. Here, minus one here. So that shows me that that cancels out, which means we have rho and then P divided by rho. Okay, we got it. Cha-ching. No, not cha-ching yet, not cha-ching yet. So we can just say P over rho equal RT, right? So we can say square root of alpha RT. Cha-ching, cha-ching, we did a QED. Okay, we're good. We can go to the next portion now. The Mach number, 1.1, propagation of regions of supersonic and subsonic and supersonic flows. Okay, so when we have V less than A, this is what happens, and we have V greater than A, this is what happens. That is true. That is correct. That is totally on point. Yes. Compressible effect associated with the fluid motion are characterized as Mach number. Yes, m equal v over a. Defined as a ratio of the velocity magnitude v equal magnitude of velocity to speed of sound a. Flow can be subsonic, sonic, or supersonic if the value of the Mach number is any of these three. Yes, that's true, respectively. Such that the propagation moves with respect to the flow with the speed of sound. Subsonic and supersonic flow show remarkable behavior. As sketched in figure 1, as can be seen. A propagation of a subsonic ends up affecting all the flow field. Instead, it propagates upstream effects fast to overcome convection. In supersonic flow, however, convection sweeps downstream the propagation, which affects the only a consial region, term the Mach cone of semi-angle alpha, such that sine alpha equal 1 divided by Mach. Yes, that's true. I don't know how else to say it. That's just true. And that's just figured out by just looking at experimental data. You can't really say much about it. Steady gas flow around the sphere. Yes. To compute a given flow field, one needs to integrate 1.1 and 1.2 together. Okay, so this is gonna be fun. With one of the alternative flow energy, 1.3, 1.7, and 1.8, with appropriate initial condition boundary to begin the introduction some needed concepts. It is of interest to consider as illustrated example the steady state to buoyant-free motion of a gas around a cylinder of radius r with negligible radiation and chemical reaction. The ambient condition in this case is given by velocity equals u infinity, which is a far stream, is along the path of the x-axis. T equal T ambient and P equal P ambient at that place. Where else the sphere surface is V equals 0, which is basically no slip condition. No slip condition, yes. No slip condition. Yeah. And T equal TW and TW is assumed to be constant. Okay, steady gas around the sphere. In this case, the problem reduces to that of integrating. Okay, so, all right. Okay, okay, okay. Oh, did we stop here? Oh, I thought this was gonna be longer. Okay, I think that's not the full picture of this question, though. Yes, it's not. Okay. We're stopping. We're not stopping here. We're definitely going to continue on that question. But we get the general idea. So we're going to stop the recording. And we're going to come back later for this thing over here. This is a beautiful thing we need to talk about, which we will. So I'm going to stop my recording. And um, do I want to give you a sneak peek? Yes, I do. This is one of my favorites. So it's just like a sneak peek on this topic over here. So we start with this over here, right? This is just continuity, beautiful continuity. And with density V bar that we have this. With that, right? Not oh yeah, actually this is different. Radius R. No, R is just this. This is not this oh, that's why he used RG. Ah, that makes sense actually. Okay, so how do you use this order shenanigans, right? You basically say, what's the biggest thing in there? So let me just write it here. It's not gonna be hard to write here, right? I have right. Let's Let's start here. Now we have density, which is just going to be density infinity is going to be the greatest point, right? Great. It's just yeah. At that point, we have u2 squared infinity, right? And divided by r. Y is divided by r. So this over here is this. So that is the length scale, and the only length scale we have is the r. So we have cha-ching, and then we have negative, and then we have Oh my God, I keep on saying cha-ching now. Oh, I'm turning into a interesting person. So we have p, and then p infinity is what it's saying, and then we have that by l, which is r in this case. Plus we have this term, right? Which has to be you've has to be I don't know actually this one. I know it has to be mu because that's mu, and then we have square square, so it has to be r squared over here, and it has to be velocity, so it's be u infinity. Okay, there you go. That should be it. And that's the same analysis we have to do continuously. Actually, this is different. Okay, this is different than I thought it would be. Anyways, then I'm gonna stop the video here because